recording in progress. Fine. All right. So, well, thank you, Giulio, for being here. And like I said, I'm glad, everything is well. We're getting worried there for a bit. I'd also like to thank all of you for your patience and for making yourselves present here today. This is just one thing before I go ahead and present Giulio. This is the last session that I'm chairing, and there is one thing I want to say, which is I want to thank Alejandro Diaz-Caro for and his team, right? In this case, it's Christian, Rafael, Daniele, and the immense amount of work that they've put into this event and FSCD and all the sort of satellite events. It's impressive. The detailed emails, the instructions. So thank you for all of that, because I know that it's a lot of work. Okay, I want to present Giulio really quickly so you can, sort of start presenting his work. So Giulio works in term rewriting, lambda calculus. Curry Howard is isomorphism. He's done his PhD between Universidad de Roma III, I think it is, and PPS. So a lot of roads lead back to PPS, by the way, when it's lambda calculus and logic, right? Which is now a RIF, by the way. So anyway, thank you for being here, and we look forward to your talk, Giulio. Just remember that you've got 45 minutes, right? We can't hear you. I can't hear you, at least. Could you double check your mic or see if your phones or your headphones are plugged in correctly? No sound.
We cannot hear you.
Do you hear me now?
Yep, you're good now. Go ahead.
Sorry, now?
Not now.
Now? Do you
now,
hear
yes,
me now?
yes, we hear you now.
Oh, okay, perfect.
Yes. Okay.
Sorry.
So the floor is yours.
Do you see my slides? Okay, so
yes.
Thank you very much for the invitation. Sorry for the delay. I had a problem with my Wi-Fi. And so first I would like to thank you, the organizers, and also the PC of this conference, because everything was absolutely fantastic. And in the past days, I really enjoyed the discussion, the talks, and there was a good interaction as well. And nowadays, this is not easy with Zoom or whatever. So I really appreciate it. So it was fantastic. So in my talk, I would like to present a line of research that I started some years ago. And so essentially, I would like to stress how a proof theoretical approach can be useful to understand the lambda calculus. In particular, how linear logic can be useful to understand lambda calculus. It can give more hints, more suggestions, more ideas. So let me start. The lambda calculus, as you know, is the model of functional programming languages and also, of course, assistants. But actually, there is not only one lambda calculus. There are many lambda calculi. For example, there are different lambda calculi depending on the evaluation mechanism that we model. We want to model call by name, call by value, call by need, for example. Or also there are many variants of the lambda calculus depending on the computational feature that the calculus aims to model. For example, non-determinism, probabilism, or infinitary, or whatever. So there are many lambda calculi in the literature, and so the fact that there exist several different paradigms somehow is troubling. Why? Because in some sense it makes each calculus it appears like arbitrary. Can we think that there is a more canonical language behind all these different dialects, all these variants? Moreover, the fact that there are many calculi, it means that each time we want to create or to define a new style of semantics, operational semantics, denotational semantics, continuation, etc., we have we always do. We always need to do that n times, each time for each variant, for each paradigm. And this is annoying in somehow. So here, what my goal I want to present is it's a sort of unifying and robust meta theory for the lambda calculi, and this meta theory is rooted on linear logic and elementary notions of reverse systems. In linear logic, because linear logic provides a sort of unifying setting for different evaluation mechanisms. And the reverse theory, on the contrary, allows us to modular and robust approach to the different variants of lambda calculi and different extensions. In this talk, also, since we are a bit late, in this talk, I would like to focus on the first point. So in the role played by linear logic and his link with the different evaluation mechanisms. As you know, linear logic was introduced years ago by Girard, and it has many, it provides many insights in different fields. In particular, it provides new concepts and ideas to study the lambda calculi. For example, the notational models of linear logic provides the notational model for lambda calculi. And in particular, linear logic allows us to study, to recognize in a very deep, accurate way the notion of resource and linearity in computation. The idea is that when we have a function from A to B, this function represents a process that consume a value of type A and transform it into a value of type B. So it really allows us to give a link between the linear notion of function coming from mathematics, analysis, algebra, and the notion of linearity coming from computer science. Moreover, thanks to that, linear logic allows us to have a quantitative study analysis of computation. So, for example, linear logic provides semantic tools to study the execution time of a program, and this is well known since the Carvalhosa PhD thesis. Also, this quantitative analysis is compatible with cost models, as shown by Benjamin Alcattoli and others in their studies about abstract machines that are clearly inspired by linear logic. And so, and there are this list of obviously is not exhaustive. There are many contributions given by linear logic to the theory of lambda calculus and in general, the theory of functional programming. Here in this talk, I want to stress the fact that linear logic also provides some hints about how to modify the syntax and the dynamics of the lambda calculi in order to get good properties. What I mean, the philosophical idea behind that is that if we let linear logic to guide the study, the design of the models of computation, then nothing can be wrong. This is, in a way, the idea. If more in general, the idea is from a theoretical perspective, let logic guide the study of models of computation. In particular, what I'm doing here is to apply this principle to the case of linear logic. So this is the idea. What is the concrete example? Let's take the plotting cobalt-value lambda calculus. Plotting cobalt-value lambda calculus has been introduced years ago, and essentially is the lambda calculus, but beta reduction is restricted to a particular case, in the sense that we can evaluate a term or a regex, or we can find a regex only when the argument is a value. So in a way is a restriction of the usual beta reduction rule. And in the literature, there are many works that show that somehow this beta V reduction is not enough, is not strong enough. Why? How we can see that? Because, for example, there are some terms that are normal for beta V, but their semantics is the same as a divergent term. And so there is a mismatch between syntax and semantics. Okay, so this is the state of the art. Now, inspired by linear logic, there are at least two proposals to extend plotting Coulomb-Value lambda calculus. One is essentially lambda calculus introduced by Acattoli and Paolini, which is a lambda calculus with explicit act at a distance. Another proposal is a Schoenfeld calculus, which is a calculus where we add to the beta, we add some commutation rules called sigma rules to beta V. And this is a calculus I introduced with Alberto Carraro some years ago. We also show that these two calculi are termination equivalent, which means that the termination in one calculus is a term in one calculus if and only if it terminates in the other calculus. So in a sense, from a semantical point of view, these two calculi are equivalent. So okay, so what's the point? What's the interest? Is that some so the first instance is that both calculi have been are some extension of the original plotting Coulomb-Value lambda calculus, and this extension has been inspired by linear logic. And what we can get, for example, in these extensions of Coulomb-Value lambda calculi, we can get a semantic characterization of normalization. So we can say that a term is normalizable in this calculi if only if is semantic is not trivial. And so this is a qualitative result that is impossible in the Plotkin's original Coulomb-Value lambda calculus because of the mismatch I mentioned at the beginning. Moreover, we can also extract some quantitative information. So, for example, we can count using semantic tools. We can count the number of steps to reach the normal form. So this is a result I proved with Benjamin Acattoli and Michael Eberle. And what I want to stress is that these results, in a way, and these calculi are not ad hoc because also we can, in the literature, there are other extensions of Coulomb-Value lambda calculi that are being inspired by I mean, they have other motivations for implementative reasons, for example, to implement, I mean, to have a model corresponding to evaluation in COP, or, for example, also for from proof theoretic reasons, there is another extension, the lambda bar mu tilde calculus, in the Coulomb-Value, in its Coulomb-Value fragment that has been introduced for proof theoretic reasons, coming from the classical sequence calculus. And all these calculi, all these extensions of Coulomb-Value lambda calculi are termination equivalent in the sense of equivalence that I said before. And so, in a way, what is interesting here? The interesting thing is that thanks to linear logic, we were able to find some new results, as, for example, the semantic characterization of normalization. And this result is not ad hoc because it's also a characterization of normalization for other calculi that are not inspired by linear logic. So it's a stronger, in this sense, it's a stronger result. So now I was talking about Coulomb-Value, the other the dual of call by value in some sense is call by name. What is the difference? Just let me explain a bit. In call by name, the idea is that we pass the argument to the calling function before evaluating it. In call by value, on the contrary, we pass the argument to the calling function after evaluating the argument. What is the difference? For example, here, if you look at this term, which is just a function that takes an argument and compute the sum of this argument by itself. So in this case, we have two possible evaluation strategies: call by name, call by value. According to call by name, we first duplicate the argument 2 times 3, and so we get 2 copies of the argument, and then we perform the arithmetic operation, and finally we get the result, which is 12. On the contrary, in call by value, we first evaluate the argument, so we first perform the 2 times 3, we get the value 6, and then we apply the function to this value, and so we get finally we get 12. So we get the same results, but with 2 different evaluations. Path. This is not only a difference between the way we get the result, because in some cases, call by name and call by value have a completely different behavior. For example, suppose that we have this term. I hope you can see my pointer. We have this term, which essentially this is a function that takes 2 arguments. This term is a function that takes 2 arguments and they discard the first one and return the second one. And we apply this argument to the a divergent program. So according to call by name, we don't evaluate the argument, so we discard it and we get the identity function, a normal form, it's fine. According to call by value, on the contrary, we first have to evaluate the argument. So we stick to the evaluation of omega, and the evaluation is diverging. It loops forever. So what I mean is that the semantics of call by name and call by value are completely different. More precisely, what are call by name and call by value? Lambda calculi. The syntax is usual. I call values variable and abstractions, and the reduction rule is beta for call by name, and is beta v for call by value. Call by v, as I told you before, is that we can apply a beta step only when the argument is a value, which means a variable or an abstraction. Of course, here we can take. We consider reductions that are. We can fire redexes everywhere. We can also consider some restrictions. For example, head reduction, which means that we can fire a beta redex that is not in an argument position for call by name, or for call by value, we can consider for also a weak reduction where that it doesn't fire a beta v redex, which is under the scope of an abstraction. Okay, as I told you before, call by name and call by value have a completely different semantics, and in general, it's impossible to derive a property for call by value from call by name or vice versa. What is the advantage of linear logic? The advantage of linear logic is that it allows us to have a uniform perspective on call by name and call by value. And I want to show you how. And to show you that, I would like to. I would like to add a little step back to proof theory. So, in particular, to Carry-Howard correspondence. You know, according to Carry-Howard, we have that proofs correspond to programs, catenation corresponds to evaluation, and there is another correspondence that Girard, the linear logic, brings to the fore, which is the fact that the different encodings of intuitionistic logic into linear logic correspond to different evaluation mechanisms. And this is the point that I want to stress now. Because actually, from linear logic, in particular from intuitionistic linear logic, we have some tools that can be studied can be used to study properties of Kolb-Anim evaluation, thanks to Girard translation of the first Girard translation of intuitionistic logic into linear logic. But also we can use a second Girard translation, which is a different translation from intuitionist logic into linear logic, into intuitionistic linear logic. And these translations allows us to study Kolb value evaluation. So this is the goal of this section of my talk. I want to show you why. What is the principle behind that? So we have these two translations, N and V. As you can guess, N is for Kolb-Anim, V is for Kolb value. What is the difference? So it doesn't matter if you don't know very well linear logic. You just have to think that linear logic introduces a new connective, the bang, and essentially this translation decorates a formula with some bang placed somewhere. The way these banks are placed in a formula are different according to for the Kolb-Anim equals 5 for the N and the V translations. So the difference is clear if we consider the arrow. So the intuitionistic arrow is translated in linear logic by the N translation by a bang followed by a linear implication. On the contrary, by Kolb value translation, by the V translation, the intuitionistic arrow is translated by a bang, the linear arrow, and another bang. Okay, so we have two ways to embed intuitionistic logic into intuitionistic linear logic, and so into proof nets. But as you know, thanks to Carry-Howard, we know very well that the simply type lambda calculus essentially correspond to the arrow fragment of intuitionistic logic, minimal logic, if you want. And in particular, the untyped lambda calculus can be seen as this fragment of intuitionistic logic, where we have just one atomic type, and the type identity O is equal to O arrow O. So the two translations N and V are actually two translations from the untyped lambda calculus into intuitionistic linear logic, and so into proof nets. Proof nets are just a graphical way to represent proofs in linear logic. Okay, so if we look at the first Girard translation, what happens? Essentially, here in this slide, you have on the left-hand side, you have natural deduction, the rules of intuitionistic natural deduction. And on the right, you have their translation in intuitionistic linear logic according to the translation N. So essentially the point is that whenever we have an arrow, this is translated by a linear arrow, and whenever we have a modus ponens, this is translated by a tensor with a cut. This is essentially the point. And of course, via Carry-Howard, this corresponds that the abstractions is translated in this way, and applications are translated in this way. What about so this was about the N translation. What's happening for the V translation? For the V translation is more or less the same, because as you can see here, abstractions, which is introduction of the implication, is translated again by the PAR rule for intuition, which is the introduction of linear implication, and the application is which is the modus ponens, is translated by a cut and a tensor. A tensor is the linear logic way to say a conjunction, the multiplicative conjunction. And so what is the difference? The difference is only in the way we use the bang. Because if we look at the end translation, we have a bang only essentially for the argument of each application. The bang is here, which means that by carry over means that the bang is only for the argument of each application. For the V translation, on the contrary, we use the bang only when we have a value, which is a variable or an abstraction. The bang is here. It's not for the application. So this is only this teeny difference between the two translations. But the difference is crucial because, for example, if we take this derivation in natural deduction, this is a derivation where there is a regex, there is a modus, an introduction of an implication and a modus ponens. So we can perform a normalization step. We get a normal form, which is this derivation here below. And what about carry over? I mean, if we look, this derivation corresponds this term of the lambda calculus. C, A, X, and B are just variable. And this other derivation corresponds to this term, A. Okay. And actually, the first term, if we perform a bit reduction step of the first term, we get exactly the second term. So what I'm saying is that, as you know very well, thanks to Carry Howard, we have that intuitionistic logic and lambda calculus correspond to each other very well. If we take a derivation, we translate it by a carry over to a lambda term, if we perform bit reduction, we get the same thing as from the starting derivation. We first perform the normalization and then we translate normal form to a lambda term. Okay, so this diagram could commute. I'm saying something is quite obvious if you know carry over. Okay, but now this is what is the relation with linear logic and the N and B translation. So now here I'm writing the translation of the first derivation here above, the translation of the first translation according to the the translation of the first the derivation according to the N translation. If we perform normalization for this derivation, what we get is this other derivation, and this other the derivation we get at the end is a normal form, which is exactly the translation of the normal form of the starting derivation. What I'm saying is just I'm saying that this diagram commute, which means that if we start from a derivation in intuitionistic logic, we first translate into linear logic via the N translation, and then we perform normalization. We get the same thing as if from the starting derivation, we first perform the normalization in intuitionistic logic, and then we translate the normal form into linear logic via the N translation. So the diagram commutes. And this is evident if we consider the lambda calculus side of the correspondence, because the first derivation corresponds to the lambda term, this lambda term, and what we get at the end is the derivation that corresponds to the lambda term, which is the term that we get after a beta step. Okay, so what I'm saying is that thanks to the N translation, everything commutes. Okay, what happens on the contrary with the V translation? With the V translation, so this is the translation of the derivation at the beginning via the B translation. If we normalize it, we get this other derivation, but this other derivation is not the translation of the normal form of the derivation of the starting derivation. What I'm saying is that this diagram doesn't commute. So, sorry, here is B. Okay. So if from the derivation we translate this derivation via the V translation, and then we perform the normalization process, we get something which is different from if we, on the contrary, we take the derivation and we first perform the normalization and then we translate the normal form. So the diagram doesn't commute. And in fact, if you look at the lambda calculus, what we get is that from the starting term, the term we get at the end, sorry, the term that we get at the end of the normalization process is not the term A. So it's a term A where we still have a sort of explicit substitution. In a way, we are saying that we are not completing, we are not performing the beta step because the argument is still there. It's not erased by the evaluation. The fact that this translation that doesn't commute is the reason why Girard called the V translation boring. Because essentially this translation doesn't perform the computation. The argument is still there. It's still there. It's not discarded. But actually, there is a reason for that. Because actually, thanks to the V translation, we can mimic the Kolbe value evaluation, not the Kolbe name evaluation. More precisely, what I'm saying is that cut elimination in linear logic simulates the beta reduction via the translation N, and the beta V reduction, the Kolbe value reduction, via the translation V. Why? Because the N translation, for the N translation, every argument is translated by a box, which means in the terms of linear logic that every argument can be duplicated or discarded, and this is exactly the discipline given by Kolbe name. On the contrary, the V translation put a box, a bang, only in for the abstractions and variables. And in fact, according to the Kolbe value discipline, only abstraction and variables can be duplicated or discarded. So in this way, this is the reason why I said that the two different encodings of intrinsic logic into linear logic correspond to different valuation mechanisms. And thanks to Girard, we can say that the study of these two evaluation mechanisms, Kolbe name and Kolbe value, are brought into the scope of the carry-over isomorphism. Okay, so now I'm saying that, okay, linear logic gives us a uniform setting, a uniform framework where we can see Kolbe name and Kolbe value. Okay, but in general, somehow, okay, the usual way to represent proofs in linear logic are proof nets, which is essentially our graphs. Somehow these graphs maybe are too general, are not easy to, are not very handled. So if you are only interested in computational aspects, maybe is this syntax of proof nets, all the stuffs given by linear logic are too much. The question is, can we internalize somehow the Girard's translation into a variant of the lambda calculus? The answer is yes. For example, the most famous work about that is this paper by Wadler and others. The idea is that, okay, we introduce a variant of the lambda calculus that is general enough so that we can embed both Kolbe name and Kolbe value lambda calculi, but the calculus is still a variant of lambda calculus, so it's very handy, very easy to reason about it. Actually, in the literature, there are many proposals of lambda calculi inspired by linear logic. that allows to embed the call by name and call by value. Here, I want to propose one more calculus inspired by linear logic, which is the bank calculus. Essentially, the idea is that in the bank calculus, we can do everything it's possible to do with the calculus introduced by Wadler and others. Somehow we can do it in a better way. Okay, so what is the bank calculus?
Sorry, Giulio, to interrupt
yes.
you have that full. We managed to move the upcoming talks because we're using the break as a buffer.
Okay.
I'd like to thank the speaker. There's just one live speaker who agreed to delay a little bit his talk. So you have you can complete your original sort of time frame. Okay.
Thank you very much. Thank you very much. Sorry again for the inconvenience. So I was talking about the bank calculus. What is the bank calculus? The bank calculus, the syntax of the bank calculus is very simple. Essentially, it's the same thing as and the usual lambda calculus, but we had two more constructors: the bank constructor and the der constructor. The difference is in the rules of this calculus, because for now the idea is that we can fire a beta regex only when the argument has a bang in front of it. Okay, so the idea is that only boxes, so I mean only resources with a bang can be duplicated or discarded. Clearly, this is an idea coming from linear logic. Somehow the der is a sort of dual of bang. Der stands for dereliction. The idea is that whenever we have a der and the argument of this der is a bang, essentially they erase each other. Essentially, we are saying that the der can open the box somehow. Okay, so the rules of the rule of the calculus is the union of these two rules. Okay. Anyway, the there is just for technical reason. The main rule is this one. Okay. Actually, we could also get rid of it. We can encode it in but anyway, it's a technical detail. Of course, the reduction here is confluent. Also, we can consider a restriction of the reduction, which is the ground reduction, which essentially allows us to fire every regex which is not under the scope of a bang. Okay, so we have the full reduction and also the ground reduction. Okay, so the reduction is confluent. I proved that. Okay, the original paper when we talked about that, it was a paper by myself and Thomas Erhard. What is the interest of this bank calculus? I recall you. Remember, there were two ways to embed. Sorry, this is a spoil. There are two ways to embed lambda calculus into linear logic via the N and V translation. Now, in a way, thanks to the bank calculus, we can decompose this translation into separate steps, which means that first we can embed the untyped lambda calculus into the bank calculus. And there are two different translations for this embedding. And then there is a canonical way to translate the bank calculus into linear logic, proofnets, and whatever. So here the focus is on this side of the composition. So from the lambda calculus into the bank calculus. What is the advantage? The advantage is that we get rid of all the things from linear logic that are very powerful, but also very general and not so handy. So I can study the two Girard translations into the bank calculus instead of proofnets. Of course, what is the idea? The idea is that the reduction in the bank calculus correspond to cut elimination in linear logic proof nets, and that the ground reduction in the bank calculus correspond to cut elimination at depth 0 in proof nets, which is the cut elimination which is not under boxes, if you know something about linear logic. Anyway, the point is that actually the bank calculus is not new at all, because the bank calculus can be seen as an untyped version of Paul-Lévy call by push value. Essentially, the bank operator corresponds to what to the tank, the call by push value calculus, and their operator correspond to the force operator in the call by push value calculus. Okay. Also, for example, there are other calculi that essentially in the literature are essentially the same as the bank calculus. For example, Simpson linear lambda calculus. So what I want to say is that bank calculus is not new as an object. It's not new. I mean, I call it bank calculus because in this way we have a nice name to a way to call it. But the important thing is not the calculus itself, it is in the way we can study the two translations into these calculus. So this is the novelty somehow. For the bank calculus, we can build a denotational model, and this is essentially we have a denotational model. I mean, we can build a denotational model for the bank calculus just starting from a denotational model of linear logic. Okay, and this is not surprising. For this part, I go a bit quickly, but the idea is that essentially essentially we can do the same thing that we did, as a similar thing that we did with linear logic compared to the lambda calculus. So we have a model of the linear logic. From this model of linear logic, we can build a denotational model of the lambda calculus. The notational model is provides an interpretation of terms which is invariant under reduction. So this is the property. We have a real denotational semantics. Okay. Now I was talking about the embedding, two embeddings of lambda calculi into the bank calculus. Okay, let's see that from a syntactic point of view. From a syntactic point of view, remember, the philosophy of the end translation was we had to add a bang for each argument. And so this is exactly what the end translation do when we translate from the lambda calculus into the bank calculus. We add a bang only for arguments. What about the B translation, the call by value translation? We add a bang. I mean, translation again is another way to translate lambda calculus into the bank calculus. We add the bank only to values, which is variables, and which are variables and abstractions. Okay, this is the main difference. So the difference is only in the way the bank are placed in a term. Actually, there is also this there, but you can't forget about it. It's just a technical operator we need, otherwise the things doesn't work, but it's not the important point. The important point is the bank. Okay, the idea again is the idea from linear logic. As I told you before, in call by name, any argument can be duplicated or discarded. This is why we add a bank for each argument via the end translation. In call by value, on the contrary, only abstractions and variables can be duplicated or discarded. And this is why we add a bank only for variables and abstractions. Okay, and so
sorry, Giulio, can I just ask you a quick question about that?
Yeah, sure.
Sorry,
sure.
Just in the previous slide.
Yeah.
So in the call by name translation. So you're thinking here of translating, say, untyped calculi, right?
Yeah, exactly.
So I don't know. So if you have something like, sort of lambda x dot xx applied to II, where creation of redexes takes place, you'll have an eye that will appear at some point in a head position, but I don't see any dereliction in the CBN translation. Is that?
Sorry, I don't understand your question.
If you have delta apply to II,
yes,
or something like that,
yeah.
so your II will be sort of placed with a dereliction, right? With a bang.
With a bang,
yeah.
Yes.
And then you'll have an eye at head position at some point in time, which will create a redix, but there will be no dereliction to remove it. You won't get stuck redixes. That's my question.
No. Okay, you didn't get stuck. You didn't get stuck, absolutely. And essentially because, well, the answer is a bit technical. The point is that we add a bang for each application. So delta applied to II becomes the translation of delta, bang, parentheses, the translation of I, bang, the translation of I.
Mm-hmm.
If you see what I mean. And thanks to that, you don't get stuck because also because maybe if you look there, what the crucial rule for reduction? When I fire Redux, I erase the box. I erase the.
Sorry.
the
yes. Okay. Yes, that answers
so
my
maybe
question.
this is the reason why.
Yes.
Now I understand your question. Okay.
Thank you.
Perfect. You're welcome. So we have, thanks to this translation, we can simulate call by name and call by value lambda calculi. For call by name, we have a result of soundness and completeness, which means that each beta step corresponds via the end translation to a reduction step in the bang calculus. But it's also, this is soundness, but we have also completeness, which means that if you take a lambda term, we translate it in the bang calculus via the end translation, and then we perform a reduction step into the bang calculus. Then what we get is the translation of a term via the end translation, and essentially I'm saying that this reduction step in the bang calculus correspond exactly to a reduction step into the lambda calculus. So what I mean is that not only we can embed the call by lambda calculus into the bang calculus, but also if we consider the fragment of the bang calculus, which is the target, the image of the end translation, what we get is essentially isomorphic to call by name. Okay, so everything we perform in this fragment of the bang calculus correspond exactly to, is just mimic something that can happen in the lambda calculus, in the call by name lambda calculus. Okay, and we have the same result for call by value via this time the V translation, not the M translation, of course. Okay, for call by value, the result is a bit more trickier for technical reason, but essentially this is the concept. Moreover, these simulations are modular in the sense that, for example, if instead of reduction, we consider only the ground reduction. Remember, the ground reduction for call by name is head reduction. The ground reduction for call by value is a weak reduction. Essentially, we have a similar soundness completeness theorem via N and D using if we focus only on the ground reduction for call by name, call by value lambda calculi, and for the bang calculus. So these results are modular, and moreover are quantity sensitive in the sense that one reduction step in the lambda calculus corresponds to one reduction step in the bang calculus. Just a little point is that these kind of results are not new. For example, in the Wadler paper, Wadler and others paper I mentioned before, we have a similar result, but completeness for call by value failed in that paper. Okay, so this is one of the reasons why I'm saying, okay, in the bang calculus we can do the same thing that can be done in other calculi inspired by linear logic, but in a better way. Because, for example, now in the bang calculus we have completeness, which is not possible in the linear calculus introduced by Wadler and others. Okay, here essentially I'm saying the same thing. What I want to say is that the lambda called by name lambda calculus and the fragment of the bank calculus, which is the image, the target of the end translation, are essentially isomorphic. One step for one corresponds exactly to one step of the other, and vice versa. And this has some consequence. For example, that the equational theories of the called by name lambda calculus and of the called by name fragment of the bank calculus are the same. Also, that normal forms are preserved by the end translation and whatever. So we have a wonderful result for call by name. For call by value, essentially, we have the same kind of results. It's a bit more trickier, but essentially, we can say that the image of the V translation in bank calculus is morally isomorphic to the call by value lambda calculus. I say morally because there are some technical details, but essentially, this is anyway. I mean, I'm not cheating. Believe me. Essentially, they are really the same. But then, if you want to talk about the technical result, we can discuss, but offline. And moreover, these results are not possible in other linear other lambda calculi inspired by linear logic, as the one given by Wouters and others. Okay, so what about the semantics? I guess I'm a bit late. So how much time I have?
You're good, Giulio, because we managed to use the coffee break as a buffer. Okay. So I'd say you have, say, 10 more minutes.
Okay.
14. Sorry, yes. So you should, yeah, that's 14 more minutes at the most.
Okay, perfect. Okay, so
sorry, I'll correct myself. I meant 10 more minutes, just to be clear. Sorry about
that. 10 more minutes. Okay, perfect. 10. So before we were talking about syntactic result, which is a bridge between the lambda calculi and call by name, call by value lambda calculi and the bank calculus. But we also have a semantic counterpart of this simulation. What do I mean? Okay, here again I'm going quite fast, but the idea is that whenever we have a model of the bank calculus, this model can also be seen as a model of call by name lambda calculus, or the call by name lambda calculus. And then, so there are, so in this, in the same abstract structure, we can interpret the usual, we can interpret the lambda calculus in the usual way, or we can do something different. So we can just take a lambda term, translate this term into the bank calculus via the n translation, and then we can interpret this term into our model according to the interpretation for the bank calculus. And so a natural question arises: what is the relation between these two ways, different ways to interpret terms? And the result is, I proved with Giulio Manzonetto, is that they are the same. Essentially, what I'm saying is that if we take a lambda term of the call by name lambda calculus, and we interpret this term in a model U, which is a model for both call by for the bank calculus and call by name lambda calculus, then this interpretation is the same as we get if we first translate the term via translation and then we interpret the term into the bank calculus. So in a way, we have this kind of nice factorization of the interpretation of lambda terms into a denotational model. And this is true. We prove that in with a categorical approach. So this means that this is true for every model for every model that is a model, essentially for every model of the bank calculus, or more precisely, for every model of the bank calculus that is constructed from a model of linear logic. Okay, so this is proved in a very general way. What happens for Kolbe value? So for Kolbe value, we have the same situation in the sense that if we take a model of the bank calculus, this model of the bank calculus can also be seen as a model for Kolbe value lambda calculus. And so again, we have two different ways to interpret terms of Kolbe value lambda calculus: the usual one and the way that first translated the term via the V translation and then interprets the term of the bank calculus we get according to the rules of the bank of the interpretation for the bank calculus. And what about the factorization? These two interpretations are the same. Actually, the answer is not. So a bit surprisingly, the two things could be interpreted are not, the two interpretations we get of the terms are not the same. So this means also that the previous result for Kolbe name wasn't trivial, because, for example, it fails for Kolbe value. I conjecture that it could be possible to to refine the result in a way that such that we can make this diagram commute, but it's an open question. It's just my conjecture. Okay, so again, morally, what I'm saying that if something works for Kolbe name is not, it doesn't mean that it automatically works for Kolbe value. And it's not, in general, Kolbe value is more difficult than Kolbe name. A lot of things doesn't work in Kolbe value. So conclusion. What I was saying that if you remember, I talked about the fact that there are many lambda calculi. In particular, for example, there are Kolbe name and Kolbe value lambda calculi, and the existence of two paradigms is troubling, because first, it seems like there is each language could appear arbitrary. And moreover, every time we want to define the semantics, we have to define twice, once for Kolbe name and once for Kolbe value. And the bank calculus is a general setting where we can compare Kolbe name and Kolbe value in the same revising system with the same denotational semantics. So it's I think it's a useful tool to compare Kolbe name and Kolbe value. And moreover, it can be used to as a tool to in order to prove some general result for both Kolbe name and Kolbe value. What do I mean? I mean that, for example, I give you some examples on some results I get with other authors. For example, factorization. What is a factorization? I mean that a factorization theorem says that whenever a term reduces to another term, we can always factorize the reduction in order to, in a way, we rearrange the steps by first performing, for example, ground steps, and then performing steps that are not ground, okay? So we can prove this factorization theorem only once for for the bank calculus, and then thanks to the translation, thanks to the fact that the Kolbe name and Kolbe value translations works well, we can derive the corresponding factorization results for Kolbe name, Kolbe value for free, just by translation. I mean, this factorization theorem we are seeing now, if we use the Kolbe name translation forth and back, we get a factorization result for the Kolbe name lambda calculus, which says that whenever a term reduces to another, we can first perform head reduction steps, and then we can perform internal steps, which is a well-known result in the theory of Kolbe name lambda calculus. And we can have an analogous result for Kolbe value. What I mean is that here we have a sort of deal, 2 for 1, or if you want, 3 for 1. We prove factorization only once, and then we get the result for free by a translation for Kolbe name and Kolbe value. Okay, and we can have other examples of this kind. For example, for normalization theorem. So we can define a normalization strategy for the bank calculus, and by a translation, this gives a normalization strategy for Kolbe name and normalization strategy for Kolbe value. What is, what is the gain? What is the advantage? The advantage is that this kind of proofs for normalization or factorizations are quite hard and difficult to prove. So we prove the factorization theorem only once in a general setting, and for free we get the corresponding results for Kolbe name and Kolbe value via translations back and forth. Another result that is due to Delia Kessner and others, I'm not involved in this result, is that they can characterize in a semantic way normalization, and they do that in the bank calculus. And then this semantic characterization is obtained by translation for Kolbe name and Kolbe value. Another work that I published with Federico Olimpieri recently is about the semantics of bank calculus. Actually, we show that this is in the bank calculus we can define semantics, which is a refinement of non-idempotent extraction types, and we can this semantics essentially is defined in a bicategorical setting using profunctors, and again by a translation this gives automatically a bicategorical semantics for Kolbe name lambda calculus, Kolbe value lambda calculus. Okay, so until now I talked about Kolbe name and Kolbe value, but there is at least one other evaluation mechanism which that is very important, very used, especially in the theory of functional programming, which is Kolbe need, which is essentially the evaluation mechanism for Haskell, for example. And what about Kolbe need? Here, this is an open question. I have no idea. So can we, if you want, can we use the bank calculus to embed also Kolbe need evaluation? I don't have an answer for the moment. The question is quite tricky. It's an open question. The point is that it's tricky because essentially Kolbe need mix some features of Kolbe name and Kolbe value. So if such a translation exists for Kolbe need, it should mix somehow Kolbe name and Kolbe need. But it's not clear how to do that. So this is really the end of my talk. If you have questions, I'm happy to answer. Thank you very much. Sorry again for the delay.
Thank you, Giulio, for your talk. Let's thank the speaker. So I'm going to clap my hands. You can just use reactions if you wish. There we go. A lot of clapping hands for you. So the floor is open for questions. You can use the raise hand feature and raise your hand if you have any questions for Giulio. All right. Well, I mean, I have a couple of questions, but I don't want to sort of invest too much time in this because we're a little late. But oh, there's one by Danielle. Sorry, I didn't see that. I'm being told I only see. Let me see if I click on participants here and I see them all. No, I don't see any reactions here. Well, if Danielle has his hand up, please go ahead and speak. I think you can unmute yourself.
Hello.
We hear you, Daniel.
Hi, Giulio. Before answering the what about Kolbe need, which would be the more difficult one to answer. What about a bank calculus with linear substitutions instead of?
Yes. Okay. I didn't defined, but I guess it should be easy to define. Exactly in the same style as the linear substitution calculus for global name, global value defined by Benjamin O'Catry. Absolutely, it should be absolutely fine. Because again, the relationship
with proofnets,
the relationship with is clear. With linear, I mean, the relationship with linear logic is clear. Is something. I mean, thanks to Beniamino, it's super clear, and it should be absolutely feasible.
Okay.
Absolutely.
Okay, so I'll just ask one short question before we end. So your analysis is heavily based on sort of on proof theory, the proof theory of linear logic, proof nets. So one thing I might imagine is perhaps regarding your question on neededness, and so, since it has something to do with sharing, is to perhaps try to consider switching to a proof theoretical presentation where some notion of sharing is possible.
Yeah, sure, of course.
So
absolutely.
Yeah, so there are some things out
absolutely.
there. I don't know anything about it, but we hear about deep inference and things like this. Perhaps
yes,
that
exactly.
Go ahead, please.
No, sorry. Yes, I totally agree. The point is that it's difficult to. I mean, it's difficult to make the deep inference approach, a linear logic approach, to make them compatible is not trivial. So, but yes, of course. So I think that somehow it's possible. Maybe it's not the bank calculus the solution. Maybe it's another variant of another calculus that is inspired not only by linear logic but also by deep inference. And but yeah, I think it's possible. And I think it would be a great achievement to have a proof theoretical understanding of Kolbe-Mead.
Okay, thank you, Giulio. Thank you for your talk. That ends the session.
Sorry.
Thank you.